Hi everyone, this is a talk for our paper, Durable Functions on UPSLA 2021. So before starting with the talk, we first want to say a few things about the collaborators in this effort. So Durable Functions is a programming model and runtime library for stateful serverless, and it supports multiple languages and can be used on Azure Serverless or elsewhere. And it is joint work between engineers, researchers, interns, and users.
Hello, UPSLA from the Durable Functions team.
So this research paper is about semantics. And so the talk is going to go a little bit like this. First, Sebastian will give us an introduction on serverless, and then I will talk some more about the specific paper.
So let's do a bit of background. What is functions as a service? Well, simply said, it's an event-driven programming model for cloud applications. Now, what does that mean? Well, it means that your application is defined as a collection of pairs of events and functions. The events can be a number of things that happen in your cloud environment, like HTTP requests coming in from some client somewhere, a queue message in some queue service, a storage blob, which is basically a file that was uploaded somewhere. It can also have periodic timers. So the list goes on. And then the function that executes is specified as a piece of code in some language of choice. And the result is obvious. When the event happens, the function should run. And the cool part is the platform handles the rest of that story. So of course, there's a server somewhere, multiple servers probably, that run these functions, but you don't have to worry about that. The servers appear and disappear as needed, and they're billed based on how much function time you're actually running. Now, something that's not as nice are the weak execution guarantees, meaning that you can't be sure that the functions run exactly once. Each event could trigger a function multiple times, and you're also not sure that these functions run to completion when they run. We'll talk more about that in a minute. Functions as a service or serverless is hot, meaning that it's very popular with cloud developers. So, while originally popularized by AWS Lambdas, all major cloud providers now have serverless offerings, and we see continuing strong growth. In research also, we have seen many publications on using serverless for computation-intensive workloads in all kinds of areas like compilation, video processing, data analysis, or for query engines. And of course, this list will go on over time. So why is serverless so popular? Well, it's about productivity, meaning how many people do you need to build and run a service? It used to be that you needed a lot, but now maybe not. So obviously, one thing is you write less code. Your application logic becomes very concise, and all the server management is delegated to the provider if you're using a hosted version of functions, or to the lower layer of your system, such as Kubernetes, if you're not running this in a hosted environment by a provider. Now, it's not just about writing less code, it's also about the properties you get from the application. And those are important things that you want in a service in the cloud, like availability. If a server fails, it needs to be replaced. You need to patch the operating systems. You need scaling so that if your load has bursts and spikes, it can be handled without you doing anything special about it. You also get the load-based billing, which is very important because most of the time services are actually idle and you don't want to pay the money for the servers if nothing is happening in your application. And the final nice thing is the analytics. So a lot of these offerings have dashboards built in that will show you how your service is doing. It will give you things like latencies, distributions, and so on. To understand the significance of functions as a service and serverless, it's good to see the larger picture. This larger picture, in my opinion, is the serverless experience being something that is needed for many, many services. So by serverless experience, I mean all of these good properties from the last slide: auto-scaling, load-based billing, availability, security, analytics, and so on. You want this not just for functions, you want it for everything. You want it for your storage database, cache, analytics, machine learning models, and yeah, just insert your own application here. Believe me, you will want these properties. Now, functions as a service has a role in this story. What is that role? The special thing about functions as a service and what makes it exciting to me is that it's not just another component. It's not just another service in your toolbox of services which grows all the time. It's the glue for those services. What I mean by that is you can now build a serverless service entirely from serverless components. So before you always needed some server to actually call the other services, but now everything in your application is actually serverless. And this does not just include serverless compute, which is functions as a service, but now your functions can call into storage. So you can have a stateful serverless service. And you can also call external services that do other things like machine learning or whatever. So you can call these from serverless and your whole application remains serverless. Your serverless experience survives the composition. And you can even have, and this is pretty typical, you can have a stateful serverless service which uses storage and also calls other external services. And this composition story, I think, is what's the real significance behind making serverless a new way of building applications.
So we saw from Sebastian how serverless is great and what it enables. Developers can finally forget everything about servers.
But wait a minute, our PL sense has started tingling. Functions as a service cure a lot of management and deployment headaches and enable composing serverless components to get full serverless applications. But the execution model is weaker, leading to correctness challenges that users have to deal with. Let's be a little bit more precise. So the functions as a service workers that compose other serverless services, like queues, tables, and storage, are ephemeral. This means that they can be killed and restarted at any point in time, and are only guaranteed to execute at least once. This leads to the following challenges. First, we have durable execution progress. What if a worker fails in the middle of execution? This means that users need to manually persist progress in the storage services so that a worker can pick up and recover if it fails from the point it was left off. The second problem is persistent application state. So workers do not have local storage, and therefore all persistent state needs to be saved in external stalls manually. Third, the third issue is exactly once processing. Workers may process events multiple times due to faults, and so developers need to ensure that some actions do not happen more than once. And finally, we have concurrency. Synchronization happens manually through these external services, and we know how hard it is to get that right as a developer. So serverless is great still, right? Well, durable functions comes to the rescue. It is a programming model for reliable, stateful, serverless. And it addresses the four challenges by offering two stateful primitives: orchestrations, which are task parallel workflows, aka the glue, and entities, which are stateful objects for persistent state. And all of this in a programming language of choice. You can choose between your favorite languages like C#, JavaScript, Python, or even PowerShell. Let's now look at an example of a durable functions orchestration, which is a thumbnail service. We can see that this orchestration starts by getting the directory from its input. This directory could be a directory in some storage service. Then it calls an activity getImageList, which internally sends a request to this storage service and gets the images in this directory. And then it has a for loop where it, for each of these images, calls an activity that creates a thumbnail and stores it somewhere else, again in some other storage service. And all of this, we wait for all of this to finish and then return the sum of all the sizes of the thumbnails. Let's now give an overview of what you will find in our paper before continuing. So first of all, there are many more durable function code examples. There is an idealized semantics that describes durable functions from the perspective of the user, hiding all of the issues of the serverless implementation. There is then a compute storage implementation semantics that describes how to implement durable functions in the presence of ephemeral compute workers and reliable storage. And there's also a proof that it implements the idealized semantics. finally, we have a replay-based implementation semantics that describes how durable functions manage to persist progress of orchestrations written in arbitrary languages, and the proof that is correct. So for the rest of the talk, we will focus on these two aspects and the intuition behind these semantics and proofs. So let's start with the compute storage implementation. In the idealized durable function semantics, workers are reliable and have their own persistent state. The reality, however, is that the friendship between computer storage is gone. They are not friends anymore, and they are separated. And so we defined an execution model that captures this. There is a variable number of stateless ephemeral workers. There is a storage system that keeps the state. And workers use this storage system to save progress in their state by communicating with it. So in this model, workers are allowed to crash before committing their progress, and they might execute the work item more than once. Therefore, this describes the actual serverless system semantics. But how can this implementation actually be equal to the idealized one? So the answer is the atomic commit. So we identify a simple but sufficient requirement on the store. The store simply needs to provide an atomic commit mechanism. Many storage services support that. For example, the Azure SQL storage service. And the intuition behind that is that a worker can use this atomic commit to commit changes to queues and state at once. Queues and state are both stored in this storage service. So if another worker has made changes, the worker fails that tried to commit. And if a worker crashes, no change happens and we're all good. So we proved that given this atomic commit, the compute storage implementation that we formalized simulates the idealized one, which has very strong exactly once execution guarantees. And what's best, the formalized compute storage implementation actually closely mirrors the durable functions SQL execution engine backend, which is a real implemented backend that exists out there and users do use. So let's now look at the replay-based implementation. In the compute storage implementation, worker progress can be serialized. In reality, however, durable function orchestrations can be written in arbitrary languages. We saw C#, JavaScript, Python, and they also support task parallel code. So their state and progress cannot be serialized by default. It could be dispersed in variables, heap objects, execution progress, and some custom solutions exist. There have been some papers in the past that study how to serialize the state and progress of some specific typed languages, for example, but they are not generalizable for arbitrary languages. So how can durable functions serialize and persist intermediate state and progress for arbitrary programming languages? The answer is that the state is saved as a history of events. The benefits are first of all, we can persist the progress of orchestrations on arbitrary languages. Second, the recovery happens by replaying the persisted history. And then another thing is that the progress persistence happens incrementally, which is fast and cheap. And another side benefit is that the history improves debuggability and observability. So a key requirement for this to work is that orchestration code needs to be deterministic. And all non-determinism therefore needs to happen in tasks that orchestrations compose. The replay-based implementation has been proven in our paper to be equivalent to the compute storage separated one, which also implies that it implements the idealized semantics. So let's sum up. Serverless has benefits, but introduces development challenges. Durable functions hides these challenges from developers with its strong idealized semantics that have very strong execution guarantees. In our paper, we show a correct implementation of durable functions in the context of compute storage separation. And a key requirement is the atomic commit, that the underlying storage needs to support an atomic commit. We then show how durable functions can serialize progress of arbitrary programming language code by representing state and progress as a history of events. If you want to learn more, you can read our paper. Thank you.